Hey everyone, welcome. Today, we're diving deep into the stuff that makes up, well, literally everything. Your phone, the air you're breathing, the most distant star in the galaxy. It all shares a fundamental secret, and we're gonna unpack it. Okay, so let me ask you something. Think about a massive burning ball of gas, millions of miles away. Now think about the invisible air filling your room, and that coffee you had this morning. What on earth could those three things possibly have in common? Well, it turns out they share one huge fundamental secret. Yep, the answer is matter. It's really that simple. Anything and everything in the universe that has mass and takes up space, from a tiny speck of dust to a whole planet like Jupiter, it's all made of matter. It is the universal Lego brick for everything we can see, touch, and even smell. Now, to really understand matter, we have to zoom in, and I mean way, way in, past anything our eyes can see, into the secret world of particles. It turns out how these unbelievably tiny particles behave is what governs everything, and it all boils down to just a few simple rules. So, rule number one is that matter isn't completely solid. Not really. On a particle level, there are these tiny invisible gaps. You've seen this happen. Think about when you stir sugar into water. The sugar just seems to disappear, right? And the water level doesn't really change? That's because those little sugar particles are just slotting themselves into the empty spaces between the water particles. Pretty cool, huh? Okay, second, these particles are never still. They're constantly in motion, vibrating, jiggling, just buzzing with what scientists call kinetic energy. And here's the key. That energy is directly tied to temperature. The hotter something is, the faster its particles are zipping around. It's why you can smell hot food from across the room, but you have to get your nose right up to a cold sandwich to smell it. The aroma particles from the hot food are literally racing through the air to get to you. So if all these particles are constantly moving, what stops everything from just flying apart? Well, that brings us to our third and final rule. Particles attract each other. There are these forces between them, kind of like tiny little magnets that pull them together. And the strength of that attraction is what makes all the difference. It's what determines whether something is a hard rock or, a flowing river. And this right here, this process called diffusion, is the perfect example of all three rules working together in real time. Just watch that ink spread through the water. The ink particles are constantly moving. That's rule number 2. They're finding their way into the empty spaces between the water particles. That's rule number 1. And the whole thing stays together as a liquid because of the attraction between all those particles, which is rule number 3. It's like a beautiful silent dance of molecule. So, now that we're in on the secret rules of particles, let's see how they create the 3 main states of matter that we see every single day. It all comes down to this constant battle between the particles' energy, their need to move, and that force of attraction, pulling them together. Okay, this table breaks it all down for us really nicely. Look at the big differences here. Solids, they've got a fixed shape, fixed volume. Liquids have a fixed volume, but they'll take the shape of whatever you pour them into. And gases, they have no rules, no fixed shape, no fixed volume. They just expand to fill up any space they're in. And check out compressibility. You can't really squeeze a solid, but you can totally compress a gas. Let's see why that is. This image shows us exactly what's going on. In a solid, over on the left, that attraction between particles is super, super strong. They're locked into this rigid grid just vibrating in place. That's what makes a solid, well, solid. But in a liquid, on the right, the particles have a bit more energy. They can break free and slide past one another, kind of like dancers on a crowded dance floor. That's what gives them their flow. And then we get to gases. Whoa. Here, the particles have so much energy that they've pretty much broken free from those forces of attraction entirely. They're just flying around like crazy, at high speeds with huge amounts of space between them. And it's all that empty space that makes gases so easy to compress. You're not squeezing the particles, you're just squeezing out the emptiness. So we've got a handle on what solids, liquids, and gases are at the particle level. But how do we get them to change from one to another? Well, it really just boils down to 2 main things we can play with: temperature and pressure. Think of this diagram as our roadmap. If you add heat, you give the particles more energy. You can melt a solid into a liquid, or even boil a liquid into a gas. Now, take that heat away, and you can condense a gas back into a liquid, or freeze a liquid solid. It's this constant cycle, all driven by energy. Okay, but here's a really interesting puzzle. When you boil a pot of water, the temperature hits 100 degrees Celsius, and then it just stops climbing. It stays at 100 degrees no matter how much you crank up the heat. So where is all that extra firepower going? It's being used for one specific job: breaking the bonds that hold the water particles together as a liquid so they can escape as a gas. This amazing hidden energy is called latent heat. It's the energy of transformation itself. Now for a really cool party trick from the world of physics. Some substances just decide to skip the liquid state altogether. You take a block of dry ice, which is just solid carbon dioxide, and it won't melt into a puddle. Nope, it just vanishes into a spooky fog. This direct jump from solid to gas is called sublimation, and it's a fantastic example of matter changing states in a very dramatic way. Okay, we've gone through a lot of the deep science, from particles to phase changes. But now, let's bring it all back home. Let's see how knowing all this stuff explains the world around us in ways you might not have realized. This simple statement explains so much. Evaporation causes cooling. Here's how it works. In any liquid, you've got some particles moving faster than others. Evaporation is when the fastest, most energetic particles at the surface manage to escape into the air. And when they leave, they take their heat energy with them, leaving the slower, cooler particles behind. The result? The liquid that's left over gets colder. It's literally nature's air conditioner. So if you want to speed up this cooling effect, you just need to speed up evaporation. And you've got 4 main levers to pull. 1, increase the surface area. 2, crank up the temperature. 3, get some wind blowing. And 4, make sure the air is dry with low humidity. Master these, and you've mastered evaporative cooling. This is a brilliant real-world example of that surface area rule. Have you ever seen an older person pour hot tea into a saucer to cool it down? They're not just being old-fashioned. They're using physics. The wide saucer exposes way more of the liquid to the air than a narrow cup does. That dramatically increases the rate of evaporation, which means it cools down way faster. Simple and so effective. And once you understand this principle, you start seeing it absolutely everywhere. Your body sweats for this exact reason. An old-school earthen pot keeps water cool because tiny amounts of water seep out and evaporate. That cold shock when you put on perfume, that's the liquid instantly evaporating off your warm skin. Even sprinkling water on a hot rooftop uses the very same idea. And here is the final piece of the puzzle. The real reason we wear cotton in the summer isn't just because it's light. It's because cotton is fantastic at absorbing water. It actually pulls sweat away from your skin and spreads it out over a larger surface area, making it easier for that sweat to evaporate. Your cotton t-shirt is basically helping your body's natural cooling system work better. So, at the end of the day, here's the big takeaway. From the biggest things in the universe, like how a star is born, to the simple feeling of a cool breeze on a hot day, it's all governed by the same simple rules, followed by these tiny, invisible particles. If you understand the small stuff, you can make sense of it all. We've covered the big 3 today, but they are not the whole story. Not by a long shot. What happens when you heat a gas to millions of degrees, creating a supercharged state of matter called plasma, like what you find in the sun? Or what happens when you cool atoms down to just a fraction of a degree above the coldest possible temperature in the universe, creating a bizarre new state called a Bose-Einstein condensate? The story of matter, it turns out, is just getting started.